Hello everyone, I'm Viral Gupta. Me and my fellow team member Yanbo will be talking about how we have built a solution to tune models online in production in a way that improves experimentation velocity and improves the overall productivity of the team. Let us start with the personal pain point we faced. We had a very good system in place to do offline machine learning. That is, we can easily iterate on several feature ideas as we have a feature library store within LinkedIn that lets us publish, subscribe to new features. After adding the features, one can train the models and look at the offline metrics. But unfortunately, like many practicing ML engineers will say, there isn't a clear way to understand the impact on business metrics without taking the models online and performing A/B tests. Today's recommendation systems optimize for multiple objectives. One way to achieve this is to build single utility models and combine them through linear combination using weights, often called as hyperparameters. In our case, it took us anywhere from 1 to 1.5 months to find a promising variant that we could ramp further. This had tremendous effect on the speed at which we could measure impact and hence operate. In this talk, we will focus on how we used approaches like Blackbox Optimization to achieve adaptive tuning capability. We'll first spend some time by going into the details of notifications recommendation system that will hopefully set the context well to look into Blackbox Optimization approach and explore exploit algorithm. We'll then look into how we build the solution as a library to enable multiple teams at LinkedIn to use it and solve similar use cases. At the end, we'll spend some time on the results. LinkedIn's mission is to connect the world's professionals and make them more productive and successful. As in the case with most social media platforms, our users access LinkedIn through mobile app. On the app, they remain updated about the activities of their professional connections through products like Newsfeed. One way to make people aware about the new content that gets created on the platform is through notifications. For instance, there's an article shared about the Lyft co-founder talking about his vision about a driverless future. If I'm someone who is interested in self-driving space, this can be a good notification candidate for me. Such notifications fall in the category of activity-based notifications because it's triggered via user activity. We realized in certain situations, users do not want to miss out on these and will like to be informed in a timely manner. For example, if my coworker just posted an article or shared an interesting article, I like to be informed about it so I can engage with it in a timely manner. This slide shows how a social activity becomes a notification. An actor has some actions such as comments, likes, post, or a repost on the news feed. Then decided by the relevance model, we fan out the activity to the recipients and will either send it as a push notification or an in-app notification. Either one will generate a badge update on top of the app icon. By seeing a pop-up message or badge update, the recipient will click the notification tab and check out what it is in the notifications. Then the user may respond to them depending on the quality of the notification. And we use these signals to train our models. It is important to talk about business metrics we care about, as we need an objective measure to evaluate effectiveness of the machine learning models deployed in our systems. As you can see, we care about improving the sessions metric. We measure this by how many users visit the site. We also care about improving the CTR metric of the notifications that we send to our members. This is directly measuring the quality of the content that we are pushing to our members. We also care about how many notifications we send to our members. One can easily send more notifications in a short term and game the system to get better metrics. But this will adversely affect the user experience and will also lead to a lot of app disables. Let's talk about the ranking function we use when we are scoring our models. For a given member M and a notification item U, the score is calculated as a linear combination of two models. The first model applied over here is p-click, which is measuring the quality of the content for a given member M and a content U. P-visit is another model, which is measuring the probability of a visit in the next T hours if the notification is sent now. We also have a threshold xth. If the score is below the threshold, we'll drop the notification, else the notification gets sent. As you can see, we need to find the appropriate values of x threshold and x alpha to to operate the system. Whatever mechanism we use to find the values, the goal is to optimize for the business metrics, as we have described in the lower part of the slide, where we care about maximizing the sessions and given with the constraints such that clicks are more than the clicks of the control model, and send volume should be less than the send volume of the control model. So some of the major challenges we face when we are doing this is most of the real-time systems are non-stationary. Optimal values of X may often vary with time, and score distributions of the models change as well, either because of the feature drift or because of the engagement on the platform. In order to learn the right values of X, you can think of it as a 2D grid where one has to manually launch multiple A/B experiments. This requires monitoring and relaunching the sum of several experiments. In short, one would agree this isn't the best use of engineering time. Let's talk about the reformulation as a black box optimization problem. So one way to model the metrics is you can think of it as for a given member I and a notification J, when we want to send the notification, we can observe the metrics and let's call it Yij. By definition, this can either be 0 or 1. So when you're sending a notification J to a member I, if the member engages in a session, the value of Yij is 1, else it is 0. What we do is we take a summation of all the Yijs and that were for all the members I that were exposed to the same value X. And we are modeling this summation of Yij as a Gaussian random variable whose mean is described by some function f of x and certain noise. The mean function can further be thought of as a Gaussian process prior, which basically means any set of points x sampled in this 2D plane are multivariate normal with a mean 0 and the variance described as an RBF kernel. Note, through this kernel, we are making the smoothness assumption. What it means is if you're observing a sessions metric at a point xi, the sessions metrics at the nearby points are correlated. How smooth the function looks can be learned through the data by using maximum likelihood principles. As can be seen over here, each metric is modeled as a separate Gaussian random variable. For sessions, we have a separate function f sessions. For clicks, we have a separate function f clicks, and for send volume, we have a separate function f sv. And what you're writing down is an original optimization problem, which is on the left side, and you can further take a Lagrange of it and create a formulation which is on the right side. And now you can solve this problem. Let's talk about the explore exploit algorithm that we use. So before we get into the exact algorithm we use, let's just look at how this whole thing works. So because you have no understanding of how these functions or how these metrics look like, you are using black box optimization. And over here, what we are seeing is we are seeing a function which is given by a dashed line. You might be interested in maximizing this function. We will observe the function at some points to identify the maximum, and it's called an explore exploit scheme. So initially, since we do not know much about the function shape, we want to explore the region and observe the function values at wider points. In the later iterations, we can exploit what we have learned so far and kind of narrowly identify the maximum of the function. The Gaussian process prior assumption on the mean function helps us model the uncertainty. So we start by observing the function at a point x, which is close to 0. This may not be very informative of the shape, but as you can see, the confidence interval decreases near the observed point. We can continue this way and observe the function at the second point, and we see the function value is lower here compared to the first point. We observe the third point, which is between the first and the second point, and you see we are slowly able to learn the shape of the function in that region. We are still less confident about the right side of the region after 5 on the x-axis. At the fourth point, we start to learn a lot about this function. Eventually, after we have learned enough by sampling different X's, maybe through a uniform distribution. Uh, these different hyperparameter configurations, we can start using it for exploiting and identifying what the maximum value of the function is. This is done using an acquisition function that optimizes the expected improvement in metrics over the current. Oftentimes, you can compute the confidence bounds, and we can look at the maximum value of the confidence bounds. As you will see, by following an explore exploit scheme, we are able to learn a good hyperparameter configuration that can give us the best business metrics that we see in the last sample that we have done over here is exploiting all the information that we have learned so far. So let's look at the exact algorithm we use in the production, which is Thompson sampling. So what we are doing over here is we are observing the metrics at different x, and we are modeling it as fk of x, where fk is different functions, either if it's an f session, f click, or fsv. Once we have observed this, we are fitting a Gaussian process on it, and we are obtaining the posterior of each f of x. We are sampling from this posterior distribution, and then we are computing a Lagrangian for the overall objective function. Once we have this, we can compute the distribution of the hyperparameters by computing the probability of each hyperparameter to be optimal. And we can continue this process in a loop until convergence. The next part of the talk will be given by Yanbo.
Next, I will talk about the infrastructure of our system. Here is a system architecture overview. When a member visits LinkedIn website, his action is tracked, including whether he clicks on notifications, visits job descriptions, and so on. This information is stored in Hadoop file systems. The utilities we are evaluating are aggregated by members. For example, aggregated click-through rate over members. Aggregated utilities and associated parameters are sent to the Bayesian optimization module. Bayesian optimization module is divided into two components, Gaussian process regressor and Thompson sampler. In high level, Gaussian process regressor is a nonlinear model fitting method, which outputs the fitted mean functions and the variance functions. Thompson sampler takes the fitted mean functions and variance functions, and outputs and suggests the distributions of parameters in the next run. After the distribution is generated, we store this information in an online parameter distribution store. When a member visits LinkedIn in the next run, a specific parameters will be chosen according to the online parameter distribution to serve him online through the UI. Next. Let me talk about the offline system in detail first. All member activities are tracked with the parameter of interest. The parameters are ETL'd into the Hadoop file system. Using the tracking data, we can generate aggregated metrics for both the objective and the constraints. The data is kept in an appropriate schema that is problem agnostic. In Bayesian optimization module, the data and the problem specifications are the input of the module. Using the data, we first estimated each of the posterior distributions of latent functions using the Gaussian process regression. Then we sample from these distributions to get the distribution of parameter x, which maximizes the objective. In the end of the Bayesian optimization module, a set of the potential parameters to be served in the next round is generated. Each one of these parameters are assigned with a probability value. When a member visits LinkedIn, his or her member ID is mapped to 0-1 interview using a hashing function. Depending on the mapping results, the system chooses the corresponding serving parameter. The parameter store can contain either the parameter value and probabilities or the member ID and the probability and the parameter values. The online systems consist of two components, parameter sampling module and the online serving module. Parameter sampling module fetches the results from the parameter serving store. When a member visits LinkedIn, this module either directly fetches his or her parameter value or computes the corresponding value from the parameter distribution as I introduced before. After the parameter value is determined, this parameter is sent to the online serving module. This module is product specific since the different products have different scoring functions. Let's take the LinkedIn's notification as an example. Whether one notification is sent to one member is determined by the following scoring functions. The online serving module implements this logic. Next. There are several design considerations I want to briefly mention here. The first, in the parameter serving module, we split the serving traffic by member IDs instead of by sessions because we want to maintain the consistency in the member experience. The second, in our offline system, the data aggregation and the Bayesian optimization flow runs in a batch mode to update the parameter distribution each hour. So our system can capture the temporary shifts quickly. Third, when we apply the Gaussian process regression on utilities, each function feeding task is independent. Right now it works well under this assumption, but it may be good to join and model all of the utilities via the multi-dimensional Gaussian process. Last, users have flexibility to set up the different constraint thresholds. For example, CTR in the treatment model should not drop more than 1% of the control. Users can easily specify this through our systems. After introducing the system architecture, we'll go over the results we obtained from the system. Let's recap the notification optimization problems. We want to tune the in-app threshold, which determines whether to send notification to members. The scoring function is a combination of the click model prediction score and the visit model prediction score. Right now, we don't tune the combination weight, but we only tune the in-app threshold. We want to maximize the sessions given the click metrics are at least as good as the control metrics, and the send volume is as good as is at most as large as the control send volume. In our system, we provide different kinds of the plots for visualization and debugging. I'll briefly show the plots here for notification output optimization problems. The first plot illustrates the output probability distribution versus the in-app threshold. This is the mean output for the Bayesian optimization module. The plot is different depending on whether the algorithm is in the exploration stage or exploitation stage. In exploration stage, the probabilities are evenly distributed. In the exploitation stage, as the plot shows here, the Thompson sampling is used to compute the probability. In this plot, the Thompson sampling is used. We can easily see that the optimal threshold is around the 0.725. Our system also provides plots like the probability of constraint feasibility to better understand the feasible regions of our search space. The higher the probability is, the more feasible the candidate is. Next. Last, we have the function fitting plots for users to understand the goodness of fit. If the utility is objective, we also provide the control max for reference. In this plot, the red curve refers to the observed matrix with optional gray lower and upper confidence band. The blue curve refers to the fitted matrix with a lower and upper confidence band, also marked as blue. The horizontal line for the objective refers to the metric of the control model. This plot illustrates the relationship between the sessions matrix versus the in-app threshold. If the utility is constrained, we also provide the lower bound and upper bound for reference. In this plot, we can see the in-app threshold increases, the click metric increases. The treatment click metric must be higher than the horizontal line if the click threshold is feasible. Similarly, we also have the plots of send volume versus in-app threshold. As the in-app threshold increases, the send volume decreases. Next. We still have a lot of interesting directions to explore, although our system is already in production. Next. First direction is that we can add on other exploit algorithms. Examples include the upper confidence bound and the expected improvement. Second, we may have limited resources to test many hyperparameters online, but the cost to test a hyperparameter offline using the sum replay pipeline is low. So the offline metrics could provide valuable prior information for the online metrics. Multitask Gaussian process models the correlation between the offline metrics and online metrics can achieve better performance. So last, the optimal parameter for different cohorts, such as the daily active users, weekly active users, may be different. Problem splitting targets on searching for the parameters for various cohorts. To sum up, in this talk, we designed and implemented a hyperparameter tuning system which progressively finds the optimal hyperparameters online. This system is actively used and tested internally in Clean, which drastically improves the developer productivities. User can easily onboard to the system and tune multiple metrics. This system is currently used by the ads, feed, notification, and people you may know. So this ends the whole presentation. Thank you.
Thank you, everyone.